The chat's up. All right, great. So confirmation that the audio sounds good. Really excited to have everybody here today. This is hopefully a nice high-level overview over machine learning things. There is the chat window over on the side, which I've pulled up here. So if there are questions that we can, of course, appreciate those and send them on over. We'll go over them at the end. But this is our opportunity to go beyond the buzzwords in machine learning, right? To actually talk a little bit about, what is machine learning, what is AI, and what is it going to mean in healthcare. And so, I'm Pedro Teixeira. I went to Harvard and Vanderbilt University School of Medicine. My specialty is biomedical informatics, machine learning, and natural language processing, or NLP, as we call it. And I, of course, do have some conflicts of interest, and that is that I'm the co-founder and CEO at PredictionHealth. I'm very proud of what we do, very biased, very excited about all the things that our team is working on. So being transparent, of course, on that. So again, just type any questions that you have into the chat, and we'll either be able to address them quickly as we go or go over all of them at the end. So first, we're going to start off with what is machine learning? And it's a subset, it's a smaller part of the overall field of artificial intelligence. And it's not what Hollywood makes it out to be. It's a little bit more mundane, but still very, very beneficial and exciting. And hopefully I can convey that well and explain it well today. We'll talk a little bit about how it works. And then most of the chat here will be about how it's going to apply to AI and what are the really exciting opportunities for applying ML and AI to help improve patient outcomes and improve our efficiency so that we can provide better and more care to more people. So machine learning is really the ultimate in pattern recognition. So you take a lot of data, a lot of examples, and ML is a set of methods that will take that raw data and identify the patterns from the examples automatically. And if you have more and more data, then you can usually train a better and smarter model. And you also have to make sure, of course, that that data is good. Since the machine learns from the examples, if you make some mistakes, if you include examples that are incorrectly labeled, that can get confusing for it. Now, there is here this simple little example we can go through. So on your left is the input, on the right the label or category. So if I told you as a human being, right, look, I have a cute fuzzy creature with a wet nose and a wagging tail, you would be able to figure out, oh, okay, that's a dog, right? And you could say, okay, well, how about a larger animal, bigger than a bread box with black and white spots and says moo? You'd be able to infer like, oh, that's probably a cow. And I could say something like, oh, well, how about this cherry red thing with 4 wheels, a steering wheel, zipping around winding roads? And you'd probably say maybe it's like a sports car or something, right? Now, that made sense to all of us, right? We're able to do that pattern matching because of our experiences in life. But if you sat down and tried to write down all of the rules to identifying many different objects and animals and creatures, it could get very difficult, right? Because 4 legs, well, it could be a goat. 2 wheels, a motorcycle or a bicycle, a skateboard with 2 wheels that have fallen off, right? And it gets very tricky to come up with all the rules for all of the corner cases that you might run into. And machine learning is really exciting because you don't have to sit down and write all the rules. You have to make a good data set, get that together, have accurate labels, but then you put that in and the machine learning algorithms figure out what are the features that separate one group for another. And that's really exciting because then you can hit a much broader set of classifications and do it much more robustly and quickly than traditional methods. So what would a machine learning workflow to actually build one of these look like? Well, you start off with your training data. So hopefully nice, clean, organized, and large with all of the classifications that you would want to do. And then, data scientists or engineers can go through, take that data, take common machine learning methods, and train up a model. That model, which internally is just doing a lot of statistics and math, which, not scary here, is figuring out how to classify new things. So you can take that model once it's trained up and put it into, a new system, a new computer, and give it examples that it has not seen before. It might be kind of similar, but it's not exactly the same thing. And it's able to infer by seeing how similar those new examples are to the previous ones it was trained on and what the labels were for what it was trained on to then make new predictions, right? So is it a picture of a cat or a dog or a car? And that is then something that can be done very quickly, very scalably, right? So if you've made some magical diagnosis engine, you could imagine new people could come in and very quickly, if you give it the data, it would be able to classify consistently over and over again, making, for example, a diagnosis. The additional layer that's kind of a more exciting and growing field within machine learning is what's called ML ops. And so just training up a really good model, and even if you get really good performance, it could be a 98, 99% accurate model, you still need to track and analyze the results that you have for different machine learning models in production. Either the system can change for some reason, your population can change over time, so they could start coming in with different diagnoses, such that the model's performance degrades over time. There's also new things that happen. So the model is kind of frozen at the point in time that it was trained. So for the last 2 years, right, COVID-19 has been a new thing. And if you had a model that was trained prior to that being something that it knew about, right, it would not be able to appropriately account for or classify that because it's outside of its worldview. So for many, many different reasons, the operations side of productionizing models needs to be thought of when you launch these models to do important tasks. And keeping in mind, again, drift of what the inputs are, right? Changing your population, model degradation for many, many different reasons. Sometimes the system can break internally when you launch things. You want to know that it's still giving you reasonably similar performance to what you had before. That can be a way to quickly identify bugs. And then just kind of keeping all that in mind and then improving the data set. So if there are new examples and you see some sort of drift, you can always take some of those new examples that weren't well classified, label them, add them to your input or your training data, and now train a new version of that model to improve performance over time. And so that's machine learning. And AI is a higher level thing that incorporates ML. So the goal with AI is to get human level problem solving, but with computers. And at the very bottom of my sort of conceptual stack there is pattern matching, which again, ML is very much this pattern matching tool. But then when you label something, there's then higher level interpretation to be done. So from that silly little example that we had earlier with the dog and the cow, there's a lot to do. There's a lot of information around what is a dog, right? That the dog barks and then the dog looks a certain way, that it has fur, that they're often friendly. Maybe sometimes they're not so friendly, right? So interpretation and then knowledge representation on top, kind of going up this stack of abstraction. And then that representation, like what is a dog? And without getting into too much of a philosophical discussion about the whole thing, there's a way or an understanding about, what is an animal? What is a car? What is a machine? What is a tool? What's a sunset? And then going from there, where you have an idea representing each one of the things that you might pattern match and then interpret as an entity, and then a way to reason about them. Right? So if you have a bowling ball and a feather, there are a lot of additional things that we realize about those. One is really heavy. One is used to play, a sport. Feather can be on an animal. So there's a lot of information around there. And to get to the point where you're able to reason and problem solve, you have to be able to understand objects in a broader context and then reason about how they would interact together. And so it becomes a very difficult problem to do something like AI. And we've seen some very exciting things and interesting results in classifying images, in predicting the next thing that you're going to type in your email or on your phone keyboard. But AI is a much, much higher level thing that incorporates a lot of levels of abstraction and hopefully in the future can help us do some very exciting things. But it's a very nuanced, complicated thing. And to add to that nuance is the fact that you need a goal. So as a human being solving for certain problems, you're going to, of course, think about what certain motivations, right? So as human beings, we have, we get hungry, we get tired. We have a lot of emotional things that drive us. The need to be near other people, right? To be appreciated, right? And those goals, which are provided to us via sort of our emotions and evolutionary processes, they are what drive us to then solve problems, right? Because you solve a problem, it is a problem because it's influencing one of the key goals that you have as an entity. So the same is true of AI. that you need to give that goals. And AI is not going to get tired or lonely, but you have to provide some sort of motivation, some sort of score or goal or motivator, so that it knows that it would then kind of have to do reasoning to apply and figure out these different problems. So again, trying to avoid getting too philosophical, we'll now go more into sort of like AI healthcare applications directly. So humans are really great at a lot of things. Empathy, understanding are very uniquely and wonderful human traits. Computers are really great at different things. Processing large amounts of data is one of those things. And so for us at Prediction Health, the belief is that you could combine the great aspects of human beings, of the clinicians, the nurse practitioners, the doctors, everyone working so hard to take care of patients, with AI, which is good at different things, and combine their abilities in a way that allows you to do even better. So the input would be patient data, and the output could be diagnoses or treatments or risk scores. And that if you do this, not only could you get to better care, but since AI is so scalable, because these models can be copy-pasted over and over again, you could have, in many ways, more accessible and more affordable care as well, which is very exciting. So, again, scalable. So once you have that model, once you've trained it up, you can copy paste it the same way you can copy paste, nearly infinite pictures of things, right? It's reproducible. So each model is an exact replica of your other models. So if you provide it the same inputs, it can give you a stable, consistent output. And sometimes you want variability and sometimes you don't. And if you're doing a good job in healthcare and you have a good model, you would want it to be consistent. And then the third category here is affordable. So you can do millions of predictions per second, right? Depending on the size of the input and how fast the server, the computer, the CPU is, or GPU is that you're running it on. And so you can have this massive throughput that's just running for the price of electricity once you've trained up the model. And again, that scale is something that enables you to make many more predictions for many more people. And hopefully, again, if the model is trained well, deliver a lot more good to a lot more people. So the future of AI in healthcare across multiple different areas, we're going to hit 3 examples now. The first, diagnostics, then personalized medicine as well. Clinician support, a lot of workflows, and for nurses, for everybody, there's an opportunity to improve workflow and efficiency within organizations there. And to have this combination of humans plus AI, we believe will be able to unlock new levels of precision, timeliness, and of course, compassion, because the less drudgery the humans have to do, the more they can focus on patients. And with a lot of the challenges and distractions in healthcare, we know that it's been harder and harder to pay the best possible attention to patients while simultaneously doing all the other things that you have to do as a clinician and healthcare provider. So example 1 is a really great study that was with collaboration with Google, and they took 128,000 retinal images, classified for whether or not they displayed evidence of diabetic retinopathy, which is one of the fastest growing causes of blindness, and trained up a deep learning network to be able to see those pictures and determine healthy versus diseased, and achieved in the range of 97-98% sensitivity and specificity. So very, very good performance. But again, I think one of the most exciting things here is that by having an ML method achieve this and do this diagnosis or this classification, it's something that's very scalable and affordable, and could take the best skills from a highly trained specialist and make it accessible to many other people. And so this study was actually done including 3 different hospitals in India, where they were able to, in these populations that were not necessarily always able to access highly trained specialists, get a highly accurate classification and monitoring for their retinal health. Now, showing the picture or not showing the picture and getting an answer of healthy versus concern for diabetic retinopathy, that's really great, but there are always deeper levels to different implementations. And so, especially in healthcare, you want to be able to understand why a decision is made. So just providing this to a black box of AI and getting a classification isn't always the most reassuring thing. What if you disagree? What if it's on the border? You want to know how confident the model is. And so understanding of machine learning predictions in many different fields is very important. So here we have the images along the side here, A through F. And then for each one, they're mapped with a heat map. And the heat map, the hotter the region, the more that portion of the image influenced the classification. So the redder it is, the more that that had something that was interesting that the model clued in on. And so across, the arteries and veins that you're seeing across the image, the optic disc, you can see that the heat map oftentimes looking at those different landmarks, right, at the irregularities, to determine whether or not there is some sort of pathology going on in the retinal image that we have before us. Now, interpretability of the models isn't a fully solved problem. It's a very big challenge, actually, in machine learning and deep learning models, especially because they're such large models that there could theoretically be very small parts or different decision points within that model that are going to potentially change the call that they will make, that given the gigantic size of the models, it can be hard to interpret, like why exactly did it do it. This is one particular method to show portions of the image that are associated with the outcome, but it's not perfect interpretability. And so anyway, very interesting, very exciting work. But keep in mind that it is possible to infer a little bit about how the decisions are made and what the confidence level is for any given ML prediction. Now, the latter portion here of our examples are going to be more in the land of voice and audio processing. And so here, we're showing a reference here for a study on taking 20 seconds of audio from a person and classifying the onset of depression with over 80% accuracy. For those of us with some experience seeing patients, you can kind of tell at times listening to somebody that there might be a concern about depression, right? Maybe more monotone, something about the speech rate can kind of come across, and there's a gestalt that you can pick up on. And that, imagine having that in a very quantifiable, computational way applied in the setting of behavioral health or psychiatry, in family medicine, where screening for that is very, very important, right? To catch these kinds of things early on. The other angle that I think is really interesting is if you're seeing someone sequentially, that you can ask their subjective experience, do you feel like your mood is better? But you could also imagine having things like this, these tools, actually scoring people to try to determine in a consistent and quantifiable way, do they seem like they're improving from some of these other markers, right? Are the voice metrics changing in a way that's consistent with the rest of the clinical picture? You can't rely on any one part, right? But it's exciting to think about being able to add metrics in many spots where currently it's so complicated that often you do have to rely on a bit of a gestalt feeling when you're talking to your patients. Now, this is a little bit of a deeper dive there, but the voice, just thinking about, when we talk to each other, there's so many different things that you can actually pull out computationally and to assess. So this study here was a review of 127 different articles, and in 2/3 of them, they actually built models and showed that different aspects of the voice, the frequency, the speech rate, jitter and shimmer, which we'll jump into in a second, actually had positive and negative correlations with other diseases like schizophrenia and anxiety. The red box being positive correlation, the more blue-green being a negative correlation, and the size of the box being how many studies were able to reproduce that result. And so you can actually see across many different studies, a fair amount of signal picked up for different diagnoses here. And jitter and shimmer, just as a very brief little review or touch, shimmer is the little variability or fluctuations, rapid fluctuations in the volume of someone's voice. Jitter being rapid fluctuations in the frequency of someone's voice. So something that's like almost imperceptible, but they can be pulled out with computational means and then used to help better eventually diagnose people and monitor their any sort of like psychiatric pathologies over time. And so the last example here I have is of course custom to Prediction Health. We take audio and we use many of our own models to do things like identifying patient versus clinician voice, extracting the words of the things that are being said, finding the medications, the diseases, the treatments that are mentioned for certain things, matching them to codes that are useful, like billing codes, and using that to interpret what's going on in the visit, to document for clinicians to free them up. And then over time, we think adding more and more really exciting methods to improve the quality of care and predictions that would help, again, process large amounts of data while freeing up clinicians to focus on their patients. And so the last tidbit we have here is the way I sort of view applying this in the future. So here in front of you, you have all your little point clouds. And on the left would be all the different documents you could pull in from a health record system. And you can see that they're clustered and labeled as nutrition, physician notes, respiratory notes, echoes, radiology reports. those clusters were made automatically by different machine learning methods that were able to take the words from all the different notes and get them to numbers, and then to cluster or predict what type of note they were by looking at labels on certain examples. On the right side, you have actually sentence by sentence predictions. So within H&P, were they talking about the family history? Were they talking about allergies? Were they talking about the plan for that patient? And you can actually really pull all of that out. And so just very briefly, just because I think it's so neat, we have these things that we run in the background, and imagine if each one of these points, instead of just being a prediction of, one disease versus another, what if they were patients? And what if you could cluster every single patient in a health system or that a clinician sees and figure out who's at risk of doing poorly or well, right? And it's kind of like the way I see things going forward, that we could use more and more of these models to identify, to process large amounts of data, and then make it actionable, right? Honing in on the groups of people that need, more help, more care. And it's just like very, very exciting. So key takeaways from today, machine learning is this great automated pattern matching. You provide examples and it figures out how to classify things automatically so that you can apply that scalably to other goals or other objectives. Artificial intelligence is not the big scary thing with the Terminator, but this stack of problem solving layers to do very, very interesting things that I think will be very key in healthcare to deliver better care and more efficient care. And finally, that combination of people and ML or AI methods is the dream team to deliver better, more compassionate, more efficient healthcare. And so with that, please feel free to ask any questions, so stick around. And then of course, if something comes to mind later on, Pedro at PredictionHealth.com, always happy to answer questions or be helpful to other folks interested in the space. So thank you. All right, looking through the question list. See if anybody has any items so far. Questions here. All right, I'm not sure if Keenan sent it here on the side.
Hey, Pedro, there's a question in the direct chat to Prediction Health.
And great.
Someone is wondering how the synthetic neural networks are built.
Yeah, so you represent each neuron in the synthetic neural network as a spot, right, with a mathematical input and output. So you basically say, with a bunch of math matrices, the equivalent is that you're going to have an input and you're going to have an output. And then that neuron is going to decide what is the threshold of input for me to sort of fire to the next one. And they're all connected together. So you do these math matrix operations where you're thresholding and they're each just kind of talking to each other. And they're synthetic because they're done with math inside of the computer, running and digitally, but they're equivalent to the neurons in your brain. They're each connecting to each other. They're sending neurotransmitters across to activate the next one. And it's not an exact mathematical number, but there is a threshold, right? Where if it gets enough signal from enough other neurons, then it too fires and then sends that signal on to other neurons. So you're literally just representing that with math inside of a computer system and then connecting them by having their signals of outputs once they fire go on to other parts, other fields, right, that represent other synthetic neurons. Hopefully that was good. Other questions?
Yeah, there's one more question in the chat. It's how to battle against those that are worried about AI that think it's not trustworthy. Ooh, good one.
Yeah, so I mean, AI all by itself, sort of referencing back to that slide about the goal, it has to be provided a goal, just the way people have to have goals. Our goals are intrinsic to sort of how we evolve. For the AI, it's really about the people that are programming the AI. And so it's not so much about worrying about that individual model. It's more in thinking about the people that are putting things together. And just as people can abuse or improperly use many other different technologies, they could theoretically do the same thing for AI. The complexity is such that it's not a terribly good tool right now if you want to cause trouble. There are a lot of other far easier things to use. But that's perhaps the key focus, right? Is what is the intent? What is the motivator that is being programmed into these different models? How are they being monitored and used? And most importantly, who's building them? and focusing there because the AI is built with the motivations and the goals that the people that design it have decided. And so that I think is really the focus. Hopefully if used properly, we can get a lot of really great things from AI. But again, it's up to us to use it responsibly. Other questions? Pop up in the chat. All right. Well, check the list here. If there are no other questions, then hope folks have a really great rest of their day. I hope that was interesting. I hope it was a good overview and that there's a little bit less mystery now and a little bit more of an understanding of what is AI, what is ML, and how it could be useful for you. If there are other questions, I'll stick around still here for a little bit. And then, seriously, Pedro at PredictionHealth.com, always happy to answer questions and be helpful to others. I think it's a really exciting tool for us to use in healthcare and many other fields. And I'm really excited to see what we can build and add to healthcare to make it better. So thank you. Thanks, Kelly. All right. Bye.